I want to talk a little bit about general op amps in this video. So you can see in this picture here is a basic op amp, and it's just modeled as basically just a high gain differential amplifier. So the two things that we use when you analyzed op amps in 240 is there are two main approximations. One is that there is no current. So in this case, I guess they put it on the bottom, I plus equals I minus equals 0. So there's no current going into these two leads. And then also the gain is really high, which means that there is a virtual short, which means V plus equals V minus. And we basically use these two approximations in order to analyze all the op amp circuits. Now, the difference between using op amps in a design sense and using op amps in an analysis sense is before you were given a circuit and you solved it. Now we have all these different circuits and we want to use them. So we're going to be talking primarily about op amp configurations in this video. So this, you can see that this file is called op amp configuration. So let's look at the basic op amp configurations. Okay, so when we use op amps, we're going to be using this negative feedback. So the simplest case is this inverting amplifier, which is given right here, which just has an R1 and an RF. And we get this equation right here for our gain, and we get an input impedance given by this and an output impedance given by that. So now we have this circuit here, which is inverting amplifier with what's called a T network. And here is the gain equation right here, and the input impedance is R1. So the advantage of this configuration is that you can change the relative input impedance relative to the gain, and so you get more flexibility. Here is your standard non-inverting configuration. Here is your gain equation, and here is your output impedance. So you see that this has a similar, first of all, it's non-inverting, and it has an infinite input impedance because we're looking into the positive terminal. So that's the advantage of this configuration over an inverting. Voltage follower is basically just a buffer. So when we look at this configuration here, what ends up happening is that my input resistance is going into one of the terminals, so it has an infinite input impedance, so Rn is equal to infinity, and we get the virtual short. So with the short across here, my output voltage is equal to my input result. So my V out equals V in. So it has unity gain. But the advantage here is that I can change my resistance here and it won't change my output resistance as long as my op amp is ideal. Summing amplifier. So if I want to add a set of voltages, I would use this configuration. So this would be something like if I'm making a mixer or I'm making a graphic equalizer and I want to add a bunch of signals together, I would use this configuration. Difference amplifier in this one, if I want to subtract two inputs, I could use this configuration. So this would be a differential amplifier. This one's kind of interesting. This one's called a switch hitter. And what you see here is you use a potentiometer right here. And this is my output equation right here. And my X varies from 0 to 1. So this can be either an inverting or a non-inverting configuration. So I can change it from being positive to negative. The instrumentation amplifier looks right here. And so the instrumentation amplifier is also a differential amplifier, but the advantage of this one is you see both of these inputs are into these terminals. So this has a very high input impedance. So this is the configuration that's used to amplify sensors and sources differentially that have a high input impedance.